All right, let's talk a little bit about solutions. Last time we finished off, we were talking about this kind of stuff, right? Yeah, in the last video. So I want to be clear. I made some clarifications in the previous class. All right, I'm going to start with the easy one. That would be covalent solutions, or covalent compounds. When I talk about solubility, generally speaking, when I talk about solubility, what I'm talking about is whether or not a compound will dissolve in water. Okay. Yes, we've talked about compounds dissolving in things that are not water, but generally speaking, when I say solubility, I'm talking about will it dissolve in water. So for covalent compounds cannot dissociate. Covalent compounds will never dissociate. All right? They're not going to fall apart. That's not a problem. So the question then is, do covalent compounds dissolve? And you answer this question by asking whether it is polar or non-polar. So if I look at methane, methane is a covalent compound, right? It's all nonmetals. Is this going to be polar or non-polar? Non-polar. So if it's non-polar, it does not dissolve. Non-polar does not dissolve. Polar compounds, like ammonia, if we drew that out, we would know that ammonia would be polar. Polar compounds dissolve. All right. So covalent do not dissociate, but they can dissolve. Okay. Now let's go to ionic compounds. For the purposes of this class, it's easy for y'all to think about these in terms of solubility rules. And I think that's probably the best way to say it. I'm going to look at the solubility rules to see if it dissociates in water. So dissociates means falls apart. So if you are said to associate with someone else, you know, Johnny associates with Bobby. That means Johnny and Bobby are hanging out together. Or maybe you're work associates. It's not typical vocabulary these days, but your work associates, you work together. So if you associate with someone, you're hanging out with them. If you dissociate, you're no longer hanging out from them. Okay? Same thing with these particles. So I'm going to use my solubility rules to decide if something is going to be soluble based on whether or not it dissociates. But only ionic compounds can dissociate. So the first thing I'm going to do, I'm going to look at this and say it is an ionic compound because I've got a metal and a nonmetal, right? So I choose ionic. Then I'm going to look at my solubility rules and realize it has potassium, a +1 alkali metal, so it's going to dissociate, so it's going to dissolve and dissociate. All right. On this one here, I'm going to look at it. This is also ionic, barium phosphate, but I look at my solubility rules and I recognize that most phosphates are going to be insoluble. That means if I pour that into water, it's just going to fall and sit at the bottom. So it's not going to dissociate, it's not going to dissolve. Y'all get me? Ionic compounds are going to dissolve and dissociate or not based on solubility rules. All right. A little bit of oversimplification, but I think it works for you guys, so that takes care of those possibilities. All right. Let's look now. As temperature increases, if you remember our rules from last class, as temperature increases, I can dissolve additional solute. I can dissolve additional solute if we're talking about solids into water or solids into liquids. This is not true for gases. So I have three different solution types. I've got a saturated solution, I've got an unsaturated solution, and a supersaturated solution. A saturated solution contains the maximum amount of solute for a given amount of solvent at a constant temperature. Basically, it's holding all of that particular solute that it could possibly hold. An unsaturated solution is one that could hold more. A supersaturated solution is a special case, and we talked about those last time in terms of these hand warmers. This is a supersaturated solution of sodium acetate, okay? And as long as I'm careful with it, it'll stay liquid. This is holding more than it's supposed to be able to hold. An example of an unsaturated solution would be one where the waiter brings you your iced tea, unsweet iced tea, sets it down at the table. That iced tea can handle having some sugar dissolved in it. So I take that iced tea and I put some sugar in it and I stir it up and all the sugar gets dissolved. Okay? I put a second pack in and I stir it up and maybe all that sugar gets dissolved too. But then I put that third pack in there and I start to stir it, and as soon as I stop, stuff falls to the bottom, right? So when I get to that point, I now have my glass here. I've got some sugar at the bottom here. This solution is said to be saturated. Once I get to that point, any additional sugar I put in there is just falling to the bottom. The stuff on the bottom is not part of the solution. That's an important concept to remember. Yes, I put the sugar in the glass, but it's not in the solution. That iced tea now is saturated. It's holding all it could possibly hold. All right? Those are the differences in the meaning there. All right, so how do I know if something is saturated or unsaturated or supersaturated? Well, I've got these little charts that will help me with this. And this is a collection of some. I think apparently someone told me that didn't copy very well in y'all's notes. So you're going to have to follow along on screen if that's the case. All right, so I've got barium hydroxide, I've got some sucrose, aluminum chloride, and I got some things down at the bottom here. Last three substances in the table. As the temperature increases, so this is a table talking about 100 grams of water. How many grams of whatever substance I care about, the solute, how many grams of that will dissolve in 100 grams of water? That's what this table is. So this is grams of some substance per 100 grams of water. What do I notice about the last three substances as I increase the temperature? What happens to solubility? Does everybody see that? At 0 degrees, I have a solubility of 0.00019, and as it gets warmer, that goes down. What do I know? Those last three substances are considered what? They're what? They're gases. And we've talked about this before, that as I increase the temperature, the solubility of gases decreases. I can dissolve less and less gas into the liquid. All right. All right. Number 2, let's look at how to read this table. Is a solution of 45 grams of potassium chloride dissolved in 100 grams of water at 50 degrees, unsaturated, saturated, or supersaturated? First of all, let's break this down. I need to know potassium chloride. So you're going to find that in the table. It's right here, KCl. The temperature I'm interested in is what? 50 degrees. So I'm going to go to 50 degrees here. I'm going to connect these, bring this over. So if I had 42.6 grams of potassium chloride in 100 grams of water, that would be considered saturated. That's as much as water could possibly hold. So if I happen to have dissolved 45 grams, this would be considered what kind of solution? This would be supersaturated, because the number I have successfully dissolved is higher than what I'm supposed to be able to dissolve. Is that good? All right. Let's take a look at another one. Y'all have these questions? See if y'all can solve this one. How about a solution of 222 grams of silver nitrate dissolved in 100 grams of water? Let's go to silver nitrate. Let's find that. That's here. 20 degrees. It's here. Bring those two down. If I have dissolved 222 grams, I'm now considered what?
Saturated.
That's saturated. This solution is holding just as much silver nitrate as it possibly can. I can't put any more in it. All right. How about the next one? So I've got potassium chlorate. It's right here. I've got 0 degrees, and I've got 3.5 grams. That is, somebody just said it, unsaturated, right here. Y'all see how to do this? Okay. Which solute has the highest solubility at 20 degrees Celsius? Did y'all get that? At 0 degrees Celsius, I can put 179 grams of sugar, right? Is that the highest one?
Yeah, but we're talking about 20 degrees. Right.
Oh, 20 degrees, yeah. So that's at 0. Yeah, so at 20 degrees it's going to be what? It's also going to be sucrose, yeah. But it's 230.9 grams, right? That's a lot of sugar. And I can put that much sugar in, that's basically the temperature of this room is about 20 degrees. In 100 milliliters of water, I can put 231 grams of sugar and have all of it dissolve. So it would just fall at the bottom. It wouldn't do anything else. Like as soon as I try to add more at 20 degrees, it would just fall at the bottom. Now if I warmed it up slightly, I could add more. And then if I cooled it down very gently, it wouldn't fall out. It would stay in there. In fact, that's, any of y'all ever make rock candy as a kid? So that's one of the ways you make it, yeah.
We tried to make it, but like it just kept failing.
Yeah, that happens a lot. It's really tricky to get going. Once you figure it out, it works. But yeah, you heat up water, you add bunches of sugar, you add more sugar, you add more sugar. Sometimes you add some food coloring, right? And you have a string, and basically what happens is it ends up collecting and crystallizing on the string. Yeah? What's that? Yeah, well, so yeah, you can boil tea and it'll pull the extracts out of the tea bags. But you can actually make your really syrupy sweet teas a whole lot easier by heating them up. The sugar will go into solution faster. You're still not exceeding the normal stuff. It's not like you're making it super saturated, but you can put a lot more in there. All right, at 50 degrees, who has the highest solubility? Yeah, silver nitrate. I can have 455 grams. Now, what do I know about silver nitrate? Why do you think that makes sense? It's what? It's ionic. And according to our solubility rules, what's the anion in this case? Nitrate. And we know that all nitrates, we consider all nitrates to be soluble. Okay? That's our solubility rules. All nitrates are going to be soluble. And so what happens is that water can completely tear these guys apart, and the silver, well, the nitrate gets surrounded by water and pulled off, and you're left with a silver ion. And so they both get surrounded by water particles or water molecules, and they support them in a suspension. So let's talk about what that looks like. So if I want to talk about like sodium chloride, my ionic compound, I put it in water, it falls apart. Here's my sodium, and it's going to have a positive charge. And y'all remember the Mickey Mouses, right? The big one is what? Oxygen. The little guys are, those are my hydrogens. So this is what's going on. There is an ion dipole attraction. The water molecules are surrounding the sodium and pulling it apart and pulling it away from the chlorine. And over here I've got the chlorine. It's got a negative charge. Okay, and there's more of those. Imagine there's more of those. These positively charged hydrogens are surrounding the chlorides, and they're pulling those guys apart. Okay, this is a fairly strong attraction. This is an ion dipole attraction here. That's what's going on. That's how these things are being able to go into solution. Okay, now those charts are nice. They get kind of busy, so we can better visualize data by plotting it on a graph. And this next section here is a graph reading skill. How many grams of sodium nitrate are dissolved at 60 degrees? So this is a simple chart. It's just sodium nitrate, so I'm going to go 60 degrees. I'm going to go up here. I'm going to come over here. So that looks pretty close to like what? I'd say about like 125. Obviously, on a multiple choice test, we're not going to be, we'll be far enough away from the answers, you'll be able to tell. You guys solve the next two. How many grams of sodium nitrate could I dissolve in 300 grams of water? 3 times that, right? 375. I just need to recognize this chart's asking about 100 grams. If I had 50 grams, I would do what? Divide by 2, right? So it would be, yeah. How many grams of, this one's kind of a tricky one. How many grams of sodium nitrate could be dissolved at 110 grams? So the original author who wrote this question was asking me to do some extrapolation. Okay? Let's do a little bit of real talk here. Assuming normal atmosphere, what happens at 100 degrees to water? So how much solid am I dissolving in that? Yeah, so I want y'all to think about real world questions. Yeah, I mean the question, they're asking me to extrapolate and go up to 200. But at that point, water's a gas and has vastly different properties because we know gas particles are far apart. If the gas particles are far apart, that means they're not able to surround the sodium like we were talking about. It just doesn't work that way. So you may have a graph question that just has data. You know, if we just stop the data at 80 and then ask you about 100, that would make sense, right? But at 110 degrees Celsius, water is boiling. So you want to be aware of that. All right. This is not typical. This is a learning chart. That's more what you're likely to see on a test. It's a chart that looks like that. The hardest part of this, for me anyway, is keeping track of the labels. So I'm going to tell you, find the label first. Whatever it is you're trying to find, whatever it is you're trying to look for, find that label first and then work backwards from there. So in this case, what solute dissolves best when the water is at 60 degrees? I'm at 60 degrees. I go all the way up. Which one's that? So this is sodium nitrate. So NaNO3 at 60 degrees. I'm always going to ask you a question at a specific temperature. At 60 degrees, sodium nitrate dissolves more. All right, here we go. So what solute has the lowest solubility at 60 degrees? Yeah, urbidium sulfate. Okay. How much ammonium chloride dissolves in 100 milliliters of water at 65 degrees? So this is the one where I would go if I would find ammonium chloride, which is here, and 65, which is here. And we mark that, and we come across, I don't know what that's at, 55, 60, something like that. Y'all see how that works? 65. Maybe we'll call it 60. Me and my super straight lines. Everybody cool with that? All right, let's see how we do on some other questions. You guys take care of those. We'll check on you in just a second. All right, let's see how we're doing. How much potassium bromide will dissolve in 500 milliliters of water that is at 45 degrees Celsius? So let's go 45. And potassium bromide looks like this line here. Okay, if I line that up, what's that look like? I'm going to call that, we'll call it 80 just to keep our math easy. So how much is going to dissolve in 500 milliliters? Right, so this would be 80 times 5 equals 400 grams. So this isn't 100, so this is, if I had 100 grams of water, I could dissolve 80 grams in it, right? But I'm not doing 100, I'm doing 500. So with 500 grams of water, I could dissolve 5 times as much because I have 5 times as much water. If I stir 150 grams of potassium nitrate in 100 milliliters of water that is at 70 degrees, will all of it dissolve? So I've got potassium nitrate. Where's that at? That's here. And I've got 70 degrees, and I'm going to go up to here, about here. Okay. And I'm going to put 150 grams in it. Will all of it dissolve? No, because 150 grams is way up here. Okay. In fact, so roughly 30 grams of it won't dissolve. Following up on that, if I stirred 200 grams of sodium nitrate in 100 milliliters of water that is at 45 degrees Celsius, how much of it won't dissolve? All right, so I've got sodium nitrate. Get rid of that. Sodium nitrate is, where are we at here? NaNO3. That's this line here. Okay, I've got 45 degrees. Sodium nitrate. Okay, so if I draw a line there, let's make our life easy. We'll call it 100. I know it's a beautiful straight line there. Is that what y'all see? Y'all see about 100 on your paper? I will tell you on this a little helpful hint. Get yourself your piece of paper and actually hold it up there. You know, one of your other pages, maybe your periodic table that you're going to have, and actually hold it across so you can see what you're doing. What's that? 95. Again, for the multiple choice portion of this, you'll have that, or if it's a free response, there's a graph. I think the table we've replaced on the test, it's a nice grid, so you can actually see all the grid lines. This is just one of these copies situations here. Okay. So I've got 95 or 100 grams. Let's say 100 because it makes my life easier. If I put 200 grams of sodium nitrate in there, how much won't dissolve? Yeah, so it's just 200 minus whatever you think will dissolve. So that would be 100 grams left over. Make sense? Okay. Good. What do I do with it? There it is. Okay. How many grams of sodium chloride dissolve in 200 milliliters of water that is at 50? Well, let's go to 50. And I have sodium chloride. Okay. And if we say that's, I don't know, what do y'all think that is? What's that? What's this one at? So this is sodium chloride at 50 degrees. So we'll call it 35. So if I say this is 35, how much will dissolve if I have 200 grams of water? 70. Y'all get this. All right, I have 100 grams of potassium nitrate in 100 milliliters of water at 100 degrees. Is this unsaturated, saturated, or supersaturated? Well, do I have 100 degrees on the chart? So first of all, I can't know for sure, but let's find out. If we assume this line continues, and that's a reasonable assumption. If we assume that that line continues, all right, and I have 100 grams, okay, is that going to be saturated, supersaturated, or unsaturated? Question?
Yeah, like you said that the water like boils after 100 degrees?
Yes.
At 100 degrees?
After 100. Well, after 100, it's all gas.
Okay.
So you can be at 100 and be all liquid. So I just put a dot there, and I continue the line up for potassium nitrate. This is one you can actually answer. Is this going to be unsaturated, saturated, or supersaturated? All right, so if you're under something, you're unsaturated. You can be under the line if you're unsaturated. Okay? If you're supersaturated, you're like Superman flying over the line. So if this is my line that's way up here, and this is my dot, the dot says this is unsaturated. The dot is under my line. I could definitely add more. I could definitely add more potassium nitrate to this. Y'all follow me? Whatever amount I ask you, graph that on the chart and see where it is in relationship to the line. All right, if I only had 50 milliliters of water as a solvent, how many grams of solid sodium chloride could I dissolve at 100 degrees? Well, again, apparently this got cut off a little bit. But what do I see about the chart at NaCl? It's pretty constant. NaCl is amazingly constant. That is why it's the major salt in our oceans. From the Arctic down to the tropics, there is pretty much the same amount of solubility for sodium chloride. This is really important. Imagine if you picked one of these other salts, like potassium nitrate, right? When it's really cold, you couldn't dissolve any. As you got to the tropics, you'd have a whole lot to deal with. Sodium chloride's pretty constant. I don't remember what the actual number is. So I'm going to assume that consistency continues. Again, I only have 50 mils, so I can only dissolve. Well, I have, if this line says, let's call it 35 grams, but that's in 100 grams of water. Yeah, so like 17.5, because I only have half the water. This is where this is coming from. So like 17.5 grams. It really ends up being slightly more than that, but that's for you guys to get the point. Does it sort of make sense how we read these? Like I said, for me, I find the hardest part is keeping track of the lines, particularly when there's like 14 or 15 of these lines all crossing each other. Okay? Okay? How many grams of sodium nitrate? You guys solved these two problems, if you haven't already. Okay. How many grams of sodium nitrate would be needed to saturate 100 milliliters of water at 65 degrees? I've got 65 degrees. Sodium nitrate's here. Come up here. What number do you guys come up with?
117.
Yeah, somewhere just kind of just underneath that 120 mark. And again, on the tests, you'll see we'll have good grid lines and easy to see. Okay. A test tube with 85 grams of potassium nitrate. Okay. With potassium nitrate in 100 milliliters of water at 40 degrees would look clear, unsaturated, clear, saturated, or similar to green Kool-Aid. All right, so let's do 40 degrees. All right. I got 85 grams, so somewhere in here. And I'm looking at potassium nitrate. So I'm going to put a little dot. I've got 85 grams in 100 milliliters of water at 40 degrees. Does everybody see where we put that dot? Everybody good on the dot? Is that dot above the line, on the line, or below the line? If it's above the line, it is super saturated. I would guess you would put cloudy, but super saturated is what I'm looking for. 85 grams of potassium nitrate. And again, you got to watch this line, because if I had 85 grams at 70 degrees, that would be unsaturated because it would be under the line. And if I had 85 grams at 55 degrees, that would be saturated. That would be right on the line. So it's very temperature dependent. Y'all follow? All right. This is true for solids. Now, most solids, just like all kind of rules in life, there's always exceptions. And most solids follow this exception that as I increase temperature, I increase solubility. Here is one of those exceptions where solubility actually decreases. What about gases? This is a chart of several different gases. I don't know if y'all can read those. That's nitrogen monoxide, oxygen, and nitrogen. What happens to gases as I increase temperature? Solubility does what? Solubility goes down. It decreases. So what kind of a relationship is that? This is an inverse relationship. That's correct. This should look very familiar. There was somebody's law we looked at last time. What properties of gases? We just did gases. What properties of gases are inversely related to each other? Pressure and volume. Pressure and volume. As I increase the pressure, I decrease the volume. And as I increase the volume, I decrease the pressure. Same thing here. As I increase the temperature, I decrease the solubility. There's less and less gas that a particular that water can hold. And again, you can see this as we get closer and closer to 100 degrees, that the ability of water to hold anything at 100, hold any gases at 100 degrees goes away. All right, let's switch gears a little bit. We'll talk about concentrations of solutions. Now, you may have heard terms like concentrated or dilute. And those are great terms. They're usually just relative to each other. And they're qualitative terms. Okay? Okay? In chemistry, though, we want to be precise, we want to be quantitative, and so we're going to use this new term, molarity.
Too many graduated cylinders and beakers where I can't put the rest of those in the dishwasher away.
Okay. Is there space down here? Okay. Then all right, so you have a formula chart. You've been introduced to a bunch of formulas. You have a formula chart, and you use your little reference sheets. So let's talk about molarity. Molarity is moles of solute over liters of solution. I want to be clear, the liters of solution is the entire volume. Don't get confused with liters of solvent. This is liters of solution. An example of this might mean 2.5 molar HCl means that I have 2 moles of HCl for every liter of solution. Okay? Important formula to remember. Let's look at the molarity of a solution that is made by dissolving 0.35 moles of ammonium iodide in 100 milliliters of solution. Again, I'm going to suggest you always write the formula, moles over liters, and figure out what might be missing. Do I have moles? Yes, I have moles, so I can go ahead and write that down. I can write 0.35 moles of ammonium iodide. Okay. Do I have liters? I don't have liters. I need to convert liters to milliliters. That's correct. And so that converts to 0.1 liters. And I divide that, this is 3.5 molarity. So I would call that 3.5 molar ammonium iodide. Yes?
Do we not have to put in like units after liters?
So
It'd be the whole solution, but
this?
yeah, but after like you put ammonium iodide on the top,
Uh-huh.
put on the bottom.
Well, it's the liters of the whole solution. Yeah, I see what you mean. Yeah. So this is, right, but it's liters of the whole mixture. So it's the water plus whatever. In this case, it's not going to add anything, but in some cases, the solute actually adds some volume. So that's what I'm pointing out. Let's look at the molarity of a solution that is made by dissolving 53.0 grams of potassium chloride in 500 milliliters of solution. Again, I want to write the formula. M equals moles over liters. Do I have moles? Nope, I do not have moles. Do you know how to get from grams to moles, though? And I do that first by writing the what? I need the formula. The formula for potassium chloride is what? That's KCl. And its molar mass is 1K and 1Cl. Probably need your calculators. All right, 74.55 grams per mole. So I can actually calculate the 53.0 grams of KCl times 1 mole of KCl over 74.55 grams of KCl. And that's going to give me how many moles? What'd you get? 0.71 moles of KCl. All right, so now I have moles. I'm going to reach over here and plug that in. 0.71 moles of KCl. Do I have liters? No, but I can get from milliliters to liters, right? So how many liters do I have? I have 0.5. Okay, and so 0.71 moles of KCl in 0.5 liters is going to equal what? 1.42 molar KCl. All I'm going to do is take the formula, I'm going to write it down, I'm going to figure out what I already have or what I need to convert to get there. These are very typical type problems where I'm going to give you grams and some amount of solution. Good? Let's look at problem 3. This asks it a little bit differently. When I'm making solutions for y'all in the lab, this is the kind of question that I'm faced with. I know you're going to need a certain volume. It needs to be at a certain concentration. How much do I need to add? So again, I want to strongly recommend you guys write this out. You don't have to, but I'm going to recommend you do. How many grams of sodium chloride are needed to make 1.5 liters of a 2 molar solution? I want to take this information and plug it back in here. Do I have molarity? Yeah, I do. So I have 2.00. Okay. What I don't have is moles. Can I use my algebra skills and answer this question? So how many moles do I need? I need 3 moles of NaCl. Am I done? Is that what the question asked? Question asked me for what? Question asked me for grams. Do I know how to get from moles to grams? That's what we're going to do. So 58.44 grams. Okay, and that's going to equal what? Does that seem reasonable? This is definitely a unit that's going to rely, you've got a lot of vocabulary, and yeah, you got to know that vocabulary. You also have a lot of simple algebra that you've got to keep track of. So it's going to work on your algebra skills. Problem 4. What volume of 1.25 molar sodium hydroxide can be prepared using 60 grams of sodium hydroxide? Go back and write our formula. M equals moles over liters. And I have 1.25 molar. Do I have moles? Can I get moles? So I've got 60 grams of NaOH. How do I get from grams to moles? By molar mass. Molar mass of sodium hydroxide is 39.998. And so that means that I have about what? 1.5 moles of NaOH. Okay? Yes?
Do we use the value that's in our calculator for like the 1.5?
Yeah, you'd use the 1 point. Yeah, I'm just writing this down. When you get all done, by the time you do sig figs, my guess is it probably won't matter. But yeah, you always want to keep your calc. Basically, when you start working a problem in your calculator, leave everything in your calculator until you're all the way done. Let's algebra this. And so this says this is liters equals 1.5 moles over 1.25 x. We'll call that x, right? So x equals, moles cancel, liter goes on top, and x is going to equal what?
1.2.
So I need 1.2 liter final solution. If I need something that has a 1.25 molar solution, and what I have is 60 grams of sodium hydroxide, I can make exactly 1.2 liters of that. Any questions on the algebra here? All right. This is all the different types of ways that we might ask you these kind of questions. Again, this is super, super important. M equals moles over liters. Moles and liters. So you're going to be asked to go from milliliters to liters, or maybe from picoliters to liters, grams to moles, moles to grams. All that stuff we've been doing since October, we got to keep doing. Okay. Next problem. Yes. If I need to dilute solutions, which is very common, it's very common that I need to dilute solutions. If I need to dilute solutions, I'm going to use this formula. M1V1 equals M2V2. This mathematically probably looks very familiar to you. We had a formula on the last test that looked like this one. What was that? Exactly. Yeah, it was the boils, right, where we had the relationship between P1, V1, P2, V2, right? In this case, the M is molarity. So I have a solution. We often have stock solutions that are very concentrated. They have a very high molarity, and I need to make a low molarity, like for you guys to work with. Okay? So I need to come up with a dilution. And this is how we do it. Volume doesn't matter as long as it's the same on both sides. So just watch out that. There's typically some questions about that. Molarity is always going to be moles per liter. And I can ask this to you all kinds of ways. Okay? And it's just algebra to solve for the missing piece, just like we did with Boyle's Law last class. Remember last class, or last unit, I could ask you initial pressure, initial volume, final pressure, final volume. I can do the same thing here with this kind of questions. So how would I prepare 100 milliliters of a 0.4 molar magnesium sulfate from an initial solution of 2.0 molar magnesium sulfate? Do I care what it is in this instance? I don't. I don't care that it's magnesium sulfate. But let's go ahead and take a look. M1V1 is M2V2. Okay? Now the question asks, how would you prepare it? All right, I've got 100 milliliters. That's my initial volume. This is V1 of a 0.4 molar, that's M1, from an initial solution of, how would I prepare that? These are actually going to be the 2's, not the initials. Okay, and so this is going to be M1. All right, let's go through this. Right, M1 is 2.0 molar. V1 is what I want. M2 is 0.4 molar. And V2 is 100 milliliters. Can y'all algebra that? V2 is going to be what? So 100 times 0.4 is 40. 40 divided by 2 is 20. So V1 equals 20 milliliters. This is in milliliters. Same units. So milliliters or liters or, okay? I mean, it could be gallons for all we care. Yeah, no, there's no, because then that would be a constant and that wouldn't matter. All right, so that's not actually what I said. What I said was, how would I prepare it? Right? So I would, this is something you write, 80 milliliters of water to make sense? I want to come up with 100 milliliters final. I'm going to take 20 milliliters of the original and I'm going to add 80 milliliters of water. That's the actual answer to this question. Because the question says, how would I prepare it? Good? Everybody clear? All right, you guys solve the next one. I'll give you all a minute here. All right, let's take a look. If I dilute 200 milliliters of a 3.5 molar solution to make a 100 milliliters of solution, what is the molarity of the dilute solution? So I typically put the more concentrated as the 1, as the initial, so M1. So I'm going to take 20, this is V1, this is M1, this is V2, and M2 is what we want. So 20 milliliters, 3.5 molar equals 100 milliliters, and M2 is what we want to find. So 20 times 3.5 is, did y'all get that? 70. And 170 divided by 100 equals 0.7. 0.7 molar. That's what we're looking for. Everybody good with that? So now we've introduced some different concepts, how to read solubility graphs. You guys also need to be sure and read and understand everything that's in this section here. It's a summary of our notes. So you really want to make sure you understand that, particularly this little chart here about what's going on in solvation. Okay. And then some things here about ionic and net ionic equations. Okay. We are going to be doing, what did I say? Pages 7 through 10. Okay. You guys should now be equipped to do 11 and 12. It will not be due, but you should be able to do it. So it's a great thing for you guys to go ahead and start working on 11 and 12 as well. It's really easy math and it shouldn't take you very long. All right. Good to go.